Hey everyone, I'm Praveen and welcome to AI Sparks, where artificial intelligence meets innovation and excitement. On this channel, we spark curiosity and ignite imagination with AI powered insights, tutorials, and explorations. From machine learning to robotics, we'll dive into the future today. Picture a chess grandmaster at a tournament. The room is silent. They don't calculate every square. They don't analyze every pawn equally. Most of the board is obvious. But when the position shifts, when a sacrifice appears, that's where the thinking explodes. Now, here's the uncomfortable truth: large language models don't do this. They think equally hard about every token, the, and, a comma, a paradigm shift, same compute, same depth, same effort. That mismatch is where the story begins. A recent paper steps directly into this gap. It's called Dynamic Large Concept Models: Latent Reasoning in an Adaptive Semantic Space by Xingwei Qu and Zhang with collaborators across industry and academia. And it asks a deceptively simple question: what if language models didn't think in tokens but in concepts? Not sentences, not grammar rules, but chunks of meaning discovered on their own. Language isn't uniform. Anyone who's read code, math, or dense technical text knows this. Some stretches are predictable filler, others introduce brand new ideas. But token level models don't know where the meaning spikes. So they waste compute on easy parts and underthink the hard ones. It's like rereading the obvious lines of a book and skimming the plot twist. That's not a scaling problem, that's an allocation problem. Here's the clever part: the model starts normally. A lightweight encoder reads tokens left to right. But instead of treating the sequence as flat, it watches how representations change. When adjacent token embeddings suddenly diverge, that's a signal, a semantic boundary. Tokens between boundaries get pulled into a single concept vector, variable length, learned from data. No predefined rules. The model has just compressed language into meaning. Now the magic happens. Instead of running deep transformers over long token sequences, the heavy compute is moved here into a concept level reasoning backbone. Shorter sequence, higher capacity, cheaper attention. This is where the model reasons, plans, connects ideas. Finally, a decoder expands those concepts back into tokens using causal cross attention. Think of it like outlining first, then writing sentences. Does this actually help? Yes, but in a very telling way. At about 4 tokens per concept, the model reallocates roughly one third of inference compute into reasoning. Under the same flops, it improves average zero shot accuracy by n 2.69% across 12 benchmarks. The biggest gains: tasks that require reasoning, got common sense in, multi step inference, and the trade off is honest. Some fine grained text tasks dip slightly. The model is choosing to think globally, not obsess locally. This wasn't free. A major pitfall: learning boundaries fully end to end sounds elegant, but it destabilizes training. The model slowly learns to stop compressing. The fix: decouple boundary decisions from the main loss and regulate compression globally across the batch. Another practical lesson: you cannot share learning rates. Token modules and concept modules scale differently. If you don't decouple them, training quietly collapses. The real takeaway isn't just this architecture, it's the shift in mindset. Scaling isn't only about more parameters or more data, it's about where thinking happens. Dynamic large concept models suggest a future where models slow down at meaning, speed through predictability, and reason at the right level of abstraction. And once models can reason over concepts, the next question becomes: what else can they learn to reason above? If you found this helpful, hit like, subscribe, and comment which AI system you want to build next. Stay sparked. See you in the next video.